related rate problems, two quantities vary at the same time. For instance, imagine you inflate a balloon. The radius will increase, and so will the volume. If you just put a little bit of air at a time, the radius will increase slowly, and so will the volume. Now, if you pump a lot of air into this balloon, the radius will increase very fast, and the volume will increase very fast. In that sense, the rate of change of the radius and the rate of change of the volume are related. This is why we call these problems related rate problems. There is no theory you need to know about those, we'll just look at examples. These problems always come with a little bit of reading. So a ladder of length 5 meters is leaning against a wall. There it is. If its base is slipping out at a rate of 1 centimeter per second, so this is going this way, how fast is the top sliding down the wall when it's 4 meters from the ground? So this point is sliding down. The first thing we will do is to rewrite the question and the answer in mathematical terms. For example, we're told that the base is slipping out at a rate of 1 centimeter per second. So 1 centimeter per second. But what is equal to 1 centimeter per second? This 1 centimeter per second measures how x changes with time. I can see this. So if I look at the unit, these are centimeters per second. It's a distance divided by time. So we're measuring how x changes with time. So that's going to be dx dt. You can really look at the units to try to do this kind of conversion from English into math. In that case here, you're dividing a distance by a time. Let's do the same thing for the question. How fast is the top slipping down the wall? So now what's changing is y. So it's going to be a dy. How fast is it changing means how is y changing with time again. So what we want here is our y changes when time changes. And again, what could guide you is the units. So probably you're wondering how fast it goes down. Probably you would want to write your answer in centimeters per second. So you want to divide by second. So it's dt at the bottom. And we want to know what this derivative is when y is equal to 4 meters. So we completed the first step, which is to rewrite the assumption and the question in terms of derivative. The second thing we will do is to choose some units. Because see here, some distances are in meters and some distances are in centimeters. It doesn't really matter which one you choose, but when you do calculation, you can't mix them. So you decide, you stick to it. Let's say that we decide to pick meters. Now in this case, for time appears only in one place and it's in seconds, so we'll take time in seconds. We ticked our second box. The next thing will be to find a relationship between the two things that vary. So we have an x which varies and a y which varies. We need a relationship between x and y. Now we'll look at this triangle and that rings a bell. There's a right angle triangle. That's Pythagoras. Let's write it down. We get x squared plus y squared is equal to 25, where x, y, and the 5 are all expressed in meters. Now our goal is to find a relationship between the derivatives, really. So what we will do is take the derivative of the relationship we just wrote with respect to time. And this way a dx dt will pop up, and so will a dy dt. When we differentiate with respect to t, now we get 2x times dx dt, the chain rule as usual, plus 2y dy dt, and the derivative of the right hand side will just be 0. Go back to the question. What we're trying to find is dy dt. So we will make dy dt the subject. In order to do that, we subtract 2x dx dt from both sides, and we get this minus 2x dx dt. And now we need to divide by the coefficient of dy dt, which is 2y. So I divide all of this by 2y dx dt. and that's minus x on y times dx dt. Not bad. Now we just need to substitute the values for x and y. The value for y is 4, and that's when we realize that the value for x hasn't been given to us, but if this is 5 and this is 4 in a right angle triangle, we can easily calculate x. We're going to be using Pythagoras. That's a very classical one. I'm sure that some of you even know by heart that if you have a side of 4 and a hypotenuse of 5, the remaining side will be 3. So we just sub in. When y is 4 meters, x is 3 meters, and dy dt is minus, so my x is 3 over y, that's a 4, and dx dt was given in the question. It was 1 centimeter per second, but hey, we said all the distances would be in meters, so we changed this into meters per second, so that's 0.01 meter per second. So the rate of change of y with respect to t is minus 0.75 times 0.01 meter per second. And since this is not very intuitive, now that we've done all our calculation, we can change unit and convert if we'd like. So we could convert this to minus 0.75 centimeter per second. Hey, we're getting something negative. Is that normal? Yes, it is. Y is this distance. So if your ladder is sliding down the wall, y is decreasing. So we do expect a negative value. In this problem, we have a 3 meter long trough, so it's that thing, that's where cows, for example, will drink. It has a triangular cross section, indeed. And it is filled with water at a rate of 0.5 cubic meters per minute. So the volume of water we put in every minute is constant. And the level of water will be rising with time. Our question is, how fast is the depth increasing when the water is 20 centimeters deep? Maybe you're wondering why we need to know that the water is 20 centimeters deep. The reason for that is, although we're pouring the same amount of water per minute, initially it's narrow, the level of the water will rise pretty fast. Now, when the trough is almost filled and you keep adding water, the level will rise, but at a much slower rate, because this is wider. Why don't you give it a try? You will learn a lot from the question you need to ask yourself when you're solving a problem. The first thing we will do is to rewrite what's given in the question and what we're trying to find using mathematical symbols. In this case, it's all about measuring how something is changing, so it will be derivatives. What's given is that the trough is filled with water at a rate of 0.5 cubic meter per minute. So these tell you how this volume of water inside the trough is changing. So what you are getting there is the rate of change of the volume with respect to time, and that's 0.5 cubic meter per minute. You could actually get that or check your work using the units. You want to be dividing cubic meters, so at the top you have a volume by a time, a volume over a time. What we want to find is how fast the depth is increasing. So the depth is this distance h, and we want to know how fast it's increasing. How fast means with respect to time. So we expect an answer which would be, for example, 1 centimeter per minute. So we expect a distance divided by a time. Combining these two ideas, we want to know how h is changing when time is changing. We need to get a result, which would be, for example, in meters per minute. We know that what we're trying to find is dh dt when h equal to 20 centimeters. The second thing we will do is to choose which units we're going to use. So time appears only in one place and is expressed in minutes, so it seems fairly natural to use minutes for time. Some of the distances are in meters, and this one is in centimeters. So we need to convert all of them, either all of them in centimeters or all of them in meters. to avoid the conversion of cubic meters into cubic centimeters, I think we'll stick with meters. Step 3 will be to find the relation between the variables of interest. But what are the variables of interest? Well, the one that's given, so that's your volume, and the one you want to find. So we're looking for a relationship between the volume and the height. To get an idea about how to approach this, I'm going to redraw only the water there. So this is only the water, so this is 3 meters, and this distance here, which is your h, is actually the distance there. So this volume is changing. When you put more water, h is increasing and the volume is increasing. So when we think about how to calculate this volume, we recognize the volume of a prism. So it would be enough to calculate the area of this triangle, and then we would multiply by 3. Okay. To calculate the area of a triangle, we need to do base times height divided by 2. So we know the height, we don't know the base. We need to find the base. We're going to need this distance. And in order to find this, we're going to be redrawing the 2 triangles, the one representing the trough and the one representing water. The trough will be black and the water will be blue. I've added the water. So I know that this distance is h, and the distance I'm interested in this one. Since it's what I'm looking for, maybe I can call it x. And it should be possible to calculate it, right? The first thing we notice is that these 2 triangles look alike. The only difference is in the size, but the shape is the same. And that reminds us of something, similar triangles. So let's use similar triangles to calculate x. This is a horizontal line and the top of the water is horizontal. So these 2 lines are parallel. So this angle and that one are corresponding angles on parallel lines. Therefore, they're equal. Similarly, these 2 angles are also corresponding angles on parallel lines, and they will be equal. Now that you know that your triangles are similar, since in the big one, the base and the height are equal, the small one is just the same one with a different size but the same shape, so the base will also be equal to the height. And that answers our question. This distance is h. Now we're ready to calculate the volume of the water. So we get phi is equal to the area of the triangle, which is base times height divided by 2, times the height of the prism, which is 3 here. So we get 3/2 of h squared. And since we decided that all our distances were in meters, this gives us cubic meters. So we managed to find a relationship between the volume and the height, as promised. The next step will be to differentiate this relation. The reason why we want to differentiate is because we know something not about the volume, but about its derivative. And we want something about h, but what we want is its derivative. So we need to get these derivatives. So let's differentiate this relation here with respect to time. So we get the derivative of volume with respect to time is equal to 3/2 is a constant. The derivative of h squared here is going to be 2h, but remember the variable is t not h, so I get dh dt by the chain rule. The 2's cancel, so I'm left with dv dt is equal to 3h times dh dt. That's a general relationship that's valid at any point in time as you're putting some water in the trough. Now we just sub in the values we're interested in. We want to know what happens when h is equal to 20 centimeters. So we just need to sub in h is equal to 20 centimeters, remembering that we decided that all the distances would be in meters, so we go back to meters. So we get dv dt is equal to 3h times dh dt. We now sub in the values. dv dt is 0.533, h is 0.2 times dh dt, which is still what I'm looking for. So in order to get dh dt by itself to make it the subject, I'm going to divide both sides by the coefficient of dh dt. And I get 0.5 divided by 3 times 0.2. In other words, 0.5 over 0.6. I multiply by 10 the top and the bottom. And I get 5 on 6. And now I remember, so at the top this is a distance. All our distances are in meters, so I get meters coming from the top. And I'm dividing by a time, and all our times are expressed in minutes. So I'm getting meters per minute. It's going to be useful to keep in mind the structure of what we did. So remember, first we rewrote what's given in the question in mathematical terms using derivative. Then we decided which units we would choose, which means we may need to convert some of the quantities which are given. At step 1, we found what were the quantities of interest. What we do now is find a relationship between them, which is what we did here, volume in terms of h. Next step, differentiate this relation, and you're going to get a relation between the derivative, which is valid at any point in time. Now, in the question, you will be told what is the point of interest. You will sub in those values, and that will solve your problem.